let's get started. The topic for today is sorry. Thank you. For today and the next two lectures, we're going to be studying Fourier series. I'd like to give, today will be an introduction explaining what they are and how you calculate them. But I thought before we do that, I ought to give at least a couple minutes oversight of why and where we're going with them and why they're coming into the course at this place at all. So the situation up to now is that we've been trying to solve equations of the form y double prime plus ay prime, constant coefficients, second order equations, and the f of t was the input. So we're considering inhomogeneous equations. This is the input. And so far, the response then is the solution equals the corresponding solution y of t, maybe with some given initial conditions to give a particular, pick out a special one, we call the response. The response to that particular input. And now, over the last few days, the inputs have been, however, extremely special. For input, the basic input has been exponential, or sines and cosines. And the trouble is, we learn how to solve those, but the point is to see those seem extremely special. Now, the point of Fourier series is to show you that they are not as special as they look. The reason is that, let's put it this way, that any reasonable f of t, which is periodic, it doesn't have to be even very reasonable. It can be somewhat discontinuous, although not terribly discontinuous, which is periodic with period, maybe not the minimal period, but some period, 2 pi. Of course, sine t and cosine t have the exact period 2 pi, but if I change the frequency to an integer frequency like sine 2t or sine 26t, 2 pi would still be a period, although it would not be the period. The period would be shorter. The point is, such a thing can always be represented as an infinite sum of sines and cosines. So it's going to look like this. There's a constant term you have to put out front. And then the rest, instead of writing, it's rather long to write unless you use summation notation, so I will. So it's a sum from n equal 1 to infinity, integer values of n, in other words, of a sine and a cosine. It's customary to put the cosine first, and with a frequency, the n indicates the frequency of the thing. And the Bn is sine nt. Now, why does that solve the problem of inputs, general inputs for periodic functions, at least if the period is 2 pi, or some multiple of 2, or some fraction of it? Well, you can think of it this way. I'll make a little table. Let's look at let's put over here the input, and here I'll put the response. Okay, suppose the input is the function sine nt. Well, there's going to be a certain, in other words, if you just solve the problem, you know how you put a sine nt here, you know how to get the answer, find a particular solution, in other words. In fact, you do it by converting this to a complex exponential and then getting the, the rigmarole we've been going through. So let's call the response something. Let's call it y. I better index it by n because it, of course, is a response to this particular periodic function. So n of t. And if the input is cosine nt, that will have a response yn. Now, I really can't call them both by the same name, so why don't we put a little s up here to indicate that that's the response to the sine, and here I'll put a little c to indicate it's the answer to the cosine. If you feed in cosine nt, what you get out is this function. Now what? Well, by the way, notice that if n is 0, that's going to take care of a constant term too. In other words, the reason there's a constant term out front is because that corresponds to cosine of 0t, which is 1. Now, suppose I input instead an cosine nt. All you do is multiply the answer by an. Same here. Multiply the input by bn. You multiply the response. That's because the equation's a linear equation. And now what am I going to do? I'm going to add them up. If I add them up for the different n's and take account also the n equals 0 corresponding to this first constant term, the sum of all these, according to my Fourier formula, is going to be f of t. What's the sum of this, the response, the corresponding responses? Well, that's going to be summation an yn ct plus bn yn, the response to the sine. That'll be the sum from 1 to infinity, and there'll be a constant, some sort of constant term here. Let's just call it C1. So in other words, if this input produces that response, and these are things which we can calculate, we're led by this formula, Fourier's formula, to the response to things which otherwise we would not have been able to calculate, namely any periodic function of period 2 pi will have as the procedure will be, you've got a periodic function of period 2 pi, find its Fourier series, and I'll show you how to do that today. Find its Fourier series, and then the response to that f of t, general f of t, will be this infinite series of functions where the y, these things are things you already know how to calculate. They're the responses to sines and cosines, and you just form the sum with those coefficients. Now, why does that work? It works by the superposition principle. So this is true. The reason I can do the adding and multiplying by constant, I'm using the superposition principle. If this input produces that response, then the sum of a bunch of inputs produces the sum of the corresponding responses. And why is that? Why can I use the superposition principle? Because the ODE is linear. It's okay since the ODE is linear. That's what makes all this work. Now, so what we're going to do today is I'll show you how to calculate those Fourier series. I will not be able to use it to actually solve any differential equation, and it'll take us pretty much all the period to show how to calculate a Fourier series. And, okay, so I'm going to solve differential equations on Monday. Wrong. I probably won't even get to it then because the calculation of a Fourier series is sufficient amount of work that you really want to know all the possible tricks and shortcuts there are. Fortunately, they're not very clever tricks. They're just obvious things. But it'll take me a period to point out those obvious things. Obvious in my sense, if not in yours. And finally, the third day we'll solve differential equations. I'll actually carry out the program. But the main thing we're going to get out of it is another approach to resonance. Because the things that we're going to be interested in are picking out which of these terms may possibly produce resonance and therefore a very crazy response. Some of the terms in the response suddenly get a much bigger amplitude than you would normally have thought they had, because it's picking out resonant terms in the Fourier series of the input. Okay, well, that's a big mouthful. Let's get started on calculate. So the program today is calculate the Fourier series. Given f of t, periodic, having 2 pi as a period, find its Fourier series. How, in other words, do I calculate those coefficients an and bn? Now, the answer is not immediately apparent, and it's really quite remarkable. I think it's quite remarkable anyway. It's one of the basic things of higher mathematics. And what it depends upon are certain things called the orthogonality relations. So this is the place where you got to learn what such things are. Well, I think it would be a good idea to have a general definition rather than immediately get into the specifics. So I'm going to call u of x u of t. I think I'll use, since Fourier analysis is most often applied when the variable is time, I think I'll stick to independent variable t all period long, if I remember to at any rate. So these are two continuous or not very discontinuous functions on minus pi. Let's make them periodic. Let's say 2 pi is a period. So functions, for example, like those guys, sine t, sine nt, sine 22t, and so on. Say 2 pi is a period. Well, I want them really on the whole real axis, not there. Defined for all real numbers. Then I say that they're orthogonal, perpendicular, but nobody says perpendicular. Orthogonal is the word. Orthogonal on the interval minus pi to pi if the integral, so two are orthogonal. So, well, these two functions. If the integral from minus pi to pi of u of t, v of t, the product is 0. That's called the orthogonality condition on minus pi to pi. Now, well, it's just a definition. I would love to go into a little song and dance now on what this definition really means and what its application, why the word orthogonal is used, because it really does have something to do with two vectors being orthogonal in the sense in which you learned it in 18.02. I'll have to put that on ice for the moment, and whether I get to it or not depends upon how fast I talk. But you'd probably prefer I talk slowly, so let's compromise. Anyway, that's the condition. And now what I say is that Fourier, that blue Fourier series, what finding the coefficients an and bn depends upon is this theorem that the collection of functions, if I look at this collection of functions, sine nt for any value of the integer n. Of course, I can assume n is a positive integer because sine of minus nt is the same as sine of nt. And cosine mt, let's give it a different, so I don't want you to think that they're exactly the same integers. So this is a big collection of functions as n runs from 1 to infinity. Here I could let m could run from 0 to infinity because cosine of 0 t means something. It's a constant 1. That any two distinct ones, two distinct, how can two things be not different? Well, you talk about two coincident roots. I'm just killing it, doing a little overkill. Any two distinct ones of these, two distinct members of the set of this collection of, I don't know, there's no way to say that. Any two distinct ones are orthogonal on this interval. Of course, they all have period. 2 pi is a period for all of them. So they form into this general category, but I'm talking about, but any two of the distinct ones are orthogonal on the interval from minus pi to pi. So, if I integrate from minus pi to pi sine of 3t times cosine of 4t dt, answer is 0. If I integrate sine of 3t times the sine of 60t, answer is 0. Same thing with two cosines, or a sine and a cosine. The only time you don't get 0 is if you integrate, if you make the two functions the same. Now, how do you know that you could not possibly get the answer 0 if the two functions are the same? If the two functions are the same, then I'm integrating square. A square is always positive. I'm integrating u squared. A square is always positive, and therefore I could not get the answer 0. But in the other cases, I might get the answer 0, and the theorem is you always do. Okay, so why is this? Well, I'm asking you, there are 3 ways to prove this. It's like many fundamental facts in mathematics. There are different ways of going about it. By the way, along with the theorem, I probably should have included, so I'm far away, but included, you might as well include because we're going to need it. What happens if you use the same function? If I take u equal to v, in that case, as I've indicated, you will not going to get the answer 0, but what you will get is, so in other words, I'm just asking, what is the sine of nt squared? That's the case when two of them are the same. I use the same function. What's that? Well, the answer is it's the same as what you will get if you integrate the cosine. Cosine squared, nt, dt, and the answer to either one of these is pi. That's something you know how to do from 1801, or the equivalent thereof. You can integrate sine squared. It's one of the things you had to learn for the whatever exam you took on methods of integration. Anyway, so I'm not going to calculate this out. The answer turns out to be pi. All right. Now, the ways to prove it are you can use trig identities. And I'm asking you in one of the early problems in the problem set, identities. Identities for the product of sine and cosine, expressing it in a form in which it's easy to integrate, and you can prove it that way. Or you can use, if you've forgotten the trigonometric identities and want to get some more exercise with complex, you can use complex exponentials. So I'm asking you to how to, in another part of the same problem, I'm asking you to do one of these at any rate using complex exponentials. And now I'm going to use a mysterious third method another way. I'm going to use the ODE. I'm going to do that because this is the method. It's not just sines and cosines which are orthogonal. There are masses of orthogonal functions out there, and the way they are discovered and the way you prove they're orthogonal is not with trig identities and complex exponentials, because those only work with sines and cosines. It is instead by going back to the differential equation that they solve, and that's therefore the method here that I'm going to use here, because this is the method which generalizes to many other differential equations other than the simple ones satisfied by sines and cosines. But anyway, that is the source. So the way the proof of these orthogonality conditions go, so I'm not going to do that, I'm going to assume that m is different from n, so that I'm not in either of these two cases. What it depends on is what's the differential equation that all these functions satisfy. Well, it's a different differential equation depending upon the value of n, but they look essentially the same. These satisfy the differential equation. In other words, what they have in common, the differential equation is y, let's call it u. It looks better. It's going to look better if you let me call it u. U double prime plus, well, n squared. So the function sine nt, cosine nt, satisfy u double prime plus n squared times u. In other words, the frequency is n, and therefore this is the square of the frequency is what you put here, equals 0. In other words, what these functions have in common is that they satisfy a differential equation that looks like that, and the only thing it's allowed to vary is the frequency, which is allowed to change. And the frequency is in this coefficient of u. Now, the remarkable thing is that's all you need to know. The fact that they satisfy that differential equation, that's all you need to know to prove the orthogonality relations. Okay, let's try to do it. Well, I need some notation. So I'm going to let un and vm be any two of the functions. In other words, I'll assume that m is different from n. For example, this one could be sine nt, and that could be sine of mt. Or this could be sine nt, and that could be cosine of mt. You get the idea. Any two of those, and the subscript indicates whether what the n or the m is that are in that. Any two, and I mean really two, distinct. Well, if I say that m is not n, then they positively have to be different. So again, it's overkill with my twosness. And what I'm going to calculate, well, first of all, from the equation, I'm going to write the equation this way. It says that u double prime is equal to minus n squared u. That's true for any of these guys. Of course, here it would be v double prime is equal to minus m squared times v. You have to make those simple adjustments. And now what we're going to calculate is the integral from minus pi to pi of u n double prime times v m dt. Now, well, just bear with me. Why am I going to do that? I can't explain why I'm going to do that, but you won't ask me the question in 5 minutes. Now, the point is, this is highly unsymmetric. The u is differentiated twice, the v isn't. So those two functions, but there's a way of turning them into an expression which looks extremely symmetric, where they're turned They're the same. And the way to do that is, I want to get rid of one of these primes here and put one on here. The way to do that is, if you want to integrate one of these guys and differentiate this one to make them look the same, that's called integration by parts. The most important theoretical method you learned in 1801, even though you didn't know that it was the most important theoretical method. Okay, we're going to use it now as the basis for Fourier series. Okay, so I'm going to integrate by parts. Now, the first thing you do, of course, when you integrate by parts is you just do the integration. You don't do the differentiation. So the first thing looks like this. And that's to be evaluated between negative pi and pi. I'm doing integration by parts between limits, minus what you get by doing both. You do both the integration and the differentiation. And again, evaluate that between limits. Now, I'm just going to BS my way through this. This is zero. This is zero. I don't care what the UNs, which UN you picked and which VM you picked, the answer here is always going to be zero. Instead of wasting 6 boards trying to write out the argument, let me wave my hands. Okay. It's clear, for example, that if V is a sign empty, of course it's 0 because the sign vanishes at both pi and minus pi. If the UN were a cosine, after I differentiated, it became a sine, and so now it's this side guy that's 0 at both ends. So the only case in which we might have a little doubt is if this is a cosine, and after differentiation, this is also a cosine. In other words, it might look like cosine, after this, cosine nt times cosine mt, but I claim that that's 0 too. Why? Because the cosines are even functions, and therefore they have the same value at both ends. So if I subtract the value evaluated at pi and subtract the value at minus pi, I get 0 because they have the same value at both ends. So by this entirely convincing argument, no matter what combination of sines and cosines I have here, the answer to that part will always be 0. So by calculation. But thought calculation, you don't have to, it's just a waste of time to write anything out. You stare at it until you agree that it's so. And now I've taken, by this integration by parts, I've taken this highly unsymmetric expression and turned it into something in which the u and the v are treated exactly alike. Well, good, that's nice, but why? Why did I go to this trouble? Okay, now we're going to use the fact that this satisfies the differential equation. In other words, that u double prime is equal to minus n. I'm sorry, I should have subscripted this. If that's the solution, then this is equal to times. You have to put in the subscript, otherwise the n wouldn't matter. All right. I'm now going to take that expression and evaluate it differently. Un double prime Vm dt is equal to, well, Un double prime, because it satisfies the differential equation, is equal to that. So what is this? This is minus n squared times the integral from negative pi to pi. And I'm replacing Un double prime by minus n squared Un. I pulled the minus n squared out, so it's Un here, and the other factor is Vm dt. Now, that's the proof. Huh? What do you mean that's the proof? Okay, well, I'll first state it, why intuitively that's the end of the argument. And then I'll spell it out in a little more detail, but the more detail you make for this, the more obscure it gets instead of simplicity. Look, I just showed you that this is symmetric in U and V after you massage it a little bit. Here I'm calculating in a different way. Is this symmetric in U and V? Well, the answer is yes or no. Is it symmetric in U and V? No. Why? Because of the n. The n favors U. We have what is called a paradox. This thing is symmetric in U and V because I can show it is, and it's not symmetric in U and V because I can show it is. It's not, I can show it's not symmetric because it favors the n. Now, there's only one possible resolution of that paradox. Both would be symmetric if what were true. Pardon? Negative pi. All right, let me write it this way. Okay, never mind. You see, the only way this can happen is if this expression is 0. In other words, the only way something can be both symmetric and non-symmetric is if it's 0 all the time. And that's what we're trying to prove, that this is 0. But instead of doing it that way, let me show you. This is equal to that, and therefore, two things, according to Euclid, two things equal to the same thing are equal to each other. So this equals that, which in turn, therefore, equals what I would have gotten. I'm just saying the symmetry a different way. What I would have gotten if I had done this calculation. And that turns out to be minus m squared times the integral from minus pi to pi of un vm dt. So these two are equal because they're both equal to this. This is equal to that. This equals that. Therefore, how can this equal that unless the integral is 0? How's that? Remember, m is different from n. So what this proves is therefore, the integral from negative pi to pi of un vm dt is equal to 0, at least if m is different from n. Now, there's one case I didn't include. Which case didn't I include? un times un is not supposed to be 0, so that case I don't have to worry about. But there is a case that I didn't. For example, something like the cosine of nt times the sine of nt. Here, the m is the same as the n. Nonetheless, I am claiming that this is 0 because these aren't the same function. One is the cosine, one's... Why is that 0? Can you see mentally that that's 0? Mentally. Well, this is trying to be, in another life, it's trying to be 1/2 of the sine of 2nt, right? And obviously, the integral of sine of 2nt is 0 between minus pi and pi, because, because you integrate it and it turns out to be 0. You integrate it to a cosine, which has the same value at both ends. Well, that was a lot of talking. If this proof is too abstract for you, I won't ask you to reproduce it on an exam. You can go with the proofs using trigonometric identities and or complex exponentials. But you ought to know at least one of those. And for the problem set, I'm asking you to fool around a little with at least 2 of them. Okay, now what has this got to do with the problem we started with originally? The problem is to explain this blue series. So our problem is, how from this am I going to get the terms of this blue series? So given f of t, 2 pi is a period, find the an and the bn. Okay, let's focus on the AN. The BN is the same. Once you know how to do one, you know how to do the other. So here's the idea. Again, goes back to something you learned at the very beginning of 1802, but I don't think it took. But maybe some of you will recognize it. So what I'm going to do is write, here's the term we're looking for. Here, this one. Okay? And there are others. They're long. It's an infinite series. It goes on forever. And now, to make the argument, I've got to put in one more term here. So I'm going to put in AK cosine KT. I don't mean to imply that that's comes, or K could be more than N, in which case I should have written it here. I could have also have used equally well sine KT, BK sine KT here, and I could have put it there. You know, this is just some other term. This is the AN. This is the one we want. And this is some other term. Okay? All right. Now, what you do is, to get the AN, what you do is you multiply everything through by, you focus on the one you want, and you, so it's dot, 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 and you multiply by cosine NT. So it's AK cosine KT times cosine NT. Of course, that gets multiplied too. But the one we want also gets multiplied. AN, and it becomes, when I multiply by cosine NT, cosine squared NT. And now, I hope you can see what's going to happen. Now what I'm going to do, oops, I didn't multiply the f of t. Sorry. It's the oldest trick in the book. I now integrate everything from minus to save, so I don't endlessly recopy. I'll integrate by putting it up in yellow chalk, and you are left to your own devices. This is definitely a colored pen type, of course. Okay? So, you want to integrate from minus pi to pi? Good, just integrate everything. Everything on the right-hand side also from minus pi to pi. Plus these other guys, just to indicate I haven't, you know, they're out there too. And now what happens? What's this? 0. Every term is 0 because of the orthogonality relations. They're all the form, a constant times cosine NT times something different from cosine NT. Sine KT, cosine KT. Or even that constant term. All of the other terms are 0, and the only one which survives is this one. And what's its value? The integral from minus pi to pi of cosine squared, I put that up somewhere. It's right here. Down there. It is pi. So this term turns into AN pi. AN dragged along, but the integral of the square of the cosine turns out to be pi. And so the end result is that we get a formula for AN. What is AN? AN is, well, AN times pi. All these terms are 0, and nothing is left but this left-hand side. And therefore, AN times pi is the integral from negative pi to pi of f of t times cosine nt dt. But that's AN times pi. Therefore, if I want just AN, I have to divide it by pi. And that's the formula for the coefficient AN. The argument's exactly the same if you want BN, but I'll write it down for the sake of completeness, as they say, and to give you a chance to digest what I've done. You know, 30 seconds to digest it. Sine NT dt. And that's because the argument's the same, and the integral of sine squared nt is also pi. So there's no difference there. Now, there's only one little caution. I have to be a little careful. This is n1, 2, and so on. And this is also n1, 2, and unfortunately, the constant term is a slight exception. We better look at that specifically, because if you forget it, you can get into gross errors. How about the constant term? Suppose I repeat the argument for that in miniature. There's a constant term plus other stuff. A typical other stuff. an cosine, let's see. How am I going to get that constant term? Well, if you think of this as sort of like a constant times, the reason it's a constant is because it's being multiplied by cosine 0t. Well, cosine 0t is 1, so that suggests I should multiply by 1. In other words, what I should do is simply integrate this from negative pi to pi, f of t dt. What's the answer? Well, this integrated from minus pi to pi is how much? Is c0 times 2 pi, right? And the other terms all give me 0. Every other term is 0, because if you integrate cosine nt or sine nt over a complete period, you always get 0. There's as much area above the axis or below, or you can look at two special cases, you know. Anyway, you always get 0. The same thing with the sine here. So the answer is that C0 is equal to, is a little special. It's not, you don't just put n equals 0 here, because then you would lose a factor of 2. So C0 should be 1 over 2 pi times this integral. Now, there are two kinds of people in the world. The ones who learn two separate formulas and the ones who just learn two separate notations. So what most people do is they say, look, I want this to be always the formula for A0. That means even when n is 0, I want this to be the formula. Well, then you're not going to get the right leading term. You're not going to get C, instead of getting C0, you're going to get twice it, and therefore the formula is, the Fourier series, therefore, isn't written this way. It's written, if you want an A0 there, calculated by this formula, then you've got to write not C0, but A0 over 2. I think you'll be happiest, if I have to give you advice, I think you will be happiest remembering a single formula for the ANs and BNs, in which case you have to remember that the constant leading term is A0 over 2 if you insist on using that formula. Otherwise, you have to learn a special formula for the leading coefficient, namely 1 over 2 pi instead of 1 over pi. Well, am I really going to calculate a Fourier series in 4 minutes? Not very likely, but I'll give it a brave college try. Anyway, you'll be doing a great deal of it, and your book has lots and lots of examples. Too many, in fact. It ruined all the good examples by calculating them for you. But I'll at least outline. Do you want me to spend 3 minutes outlining a calculation? You know, just so you have something to work on in the next boring class you're in. Let's see. So I'll just put a few key things on the board. I would advise you to sit still for this. Otherwise, you're going to hack it and, you know, take twice as long as you should, even though I know you've been up till 3 o'clock in the morning doing your problem set. Cheer up. I got up at 6 o'clock in the morning to make up the new one, so we're even. No, this should be 0 here. Okay. So here's minus pi. Here's pi. Here's 1, negative 1. The function starts out like that, and now to be periodic, it then has to continue on in the same way. So I think that's enough of its path through life to indicate how it runs. This is a typical square wave function, sometimes it's called. It's an odd function. It goes equally above and below the axis. Now, the integrals, when you calculate them, the an is going to be okay, look, the an is going to turn out to be 0. Let me instead, and you'll get that with a little hacking. That won't too bad. I'm much more worried about what you'll do with the bn's. Also, next Monday, you'll see intuitively that the an is 0, in which case you won't even bother trying to calculate it. How about the bn, though? Well, you see, because the function is discontinuous, so this is my input. My f of t is that orange discontinuous function. The bn is going to be, I have to break it into 2 parts. In the first part, the function is negative 1, and there I will be integrating from minus pi to pi of the function, which is minus 1, times sine of nt dt. And then there's another part, minus pi to 0. The other part I integrate from 0 to pi of what? Well, f of t is now plus 1, and so I simply integrate sine nt dt. Now, each of these is a perfectly simple integral. The only question is how you combine them. Anyway, so this is, after you calculate it, will be 1 minus cosine n pi over all over n. And this part will turn out to be 1 minus cosine n pi over n also. And therefore, the answer will be 2 minus 2 cosine, 2 over n, 2 over n times, right? 2 minus 2 times 1 minus cosine n pi over n. Now, okay, now what's this? This is minus 1 if n is odd. It's plus 1 if n is even. Now, either you can work with it this way, or you can combine the two of them into a single expression. It's minus 1 to the nth power. Takes care of both of them. But the way the answer is normally expressed, it would be minus 2 over n times, if n is even, I get 0. If n is odd, I get 2. So times 2 if n is odd, and 0 if n is even. So it's 4 over n, or it's 0, and the final series is a sum of those coefficients times the appropriate cosine or sine? Sine terms, because the cosine terms were all coefficients, all turned out to be 0. I'm sorry I didn't have a chance to do that calculation in detail, but I think that's enough sketch for you to be able to do it, the rest of it yourself.